All right, good afternoon, everyone. Anyway, let's do one final go around with the photoelectric effect. Whenever electrons are ejected from a metal surface due to the absorption of EMR, which is usually light, visible light, but it could be, as you see in this diagram, ultraviolet radiation. That's called the photoelectric effect. The light is absorbed. Something happens on the surface atoms of the piece of metal to kick electrons out. The photoelectric effect doesn't occur unless the frequency of the light hitting the metal is greater than what's called the threshold frequency of the metal. The reason why this is the case is because when the frequency of the light is lower than the threshold frequency, each photon has less energy than the work function. But if the frequency of the radiation is greater than the threshold frequency of the metal, then the reason electrons are kicked out is that the photons within that light source have more energy than the work function. And kind of getting ahead of myself here in terms of the explanation of the photoelectric effect, why that's an important idea is that when the photons strike the metal, each photon is absorbed by one electron. Going on the heels of that, if each photon gets absorbed by a single electron, then it makes sense that if you had more photons striking the metal, then you will get more electrons being ejected. So when we talk about the brightness of the light or the intensity of the light, not the frequency, the brightness or the intensity of the light, we're really talking about how many photons there are packed together in a certain area. So if something is twice as bright, that means there's twice as many photons striking the metal at any point in time. And if you have more photons, you're going to get more electrons. Again, we haven't talked about this in a couple of days, but I don't really know that it's on this page, but it's definitely on the handout I gave you. More electrons would be measured by seeing a greater current. Okay. These are all kind of discoveries by Millikan, and the explanations are credited to Einstein. If the photoelectric effect occurs, say, with orange light, which means the frequency of orange light is greater than the threshold frequency, and then you shine a different color light on the same metal, but the different color has a higher frequency or a shorter wavelength, then what happens is you get just as many electrons being ejected, but each electron has more kinetic energy. And I don't know, I guess it is on there. You know there's more kinetic energy because you see a greater stopping voltage. There's a greater voltage required to stop them. Millikan also discovered that there's a mathematical relationship between the frequency of the light causing electron ejection and the kinetic energy of the electrons, and the graph looks like that. The slope of all of these lines is the same, even though they have different threshold frequencies. The threshold frequencies are given by the x-intercepts, or I guess I should say f-intercepts, the horizontal variable intercept. The explanation for the photoelectric effect, as well as any equations that we can use, are all kind of visible here. The photon gives all of its energy to an electron. The electron then has that energy, which I'm calling HF at the top. The electron loses a certain amount of energy that's determined by the metal, or by the threshold frequency of the metal, and whatever's left over is kinetic energy. So you can use all of these other formulas to build an equation that can allow you to solve a problem. These two formulas on the left for EK have to be in joules. So one last kind of kick at the cat. There's your graphical analysis. Take a look at your work from either part of the practice. There was, I think, on page 47 maybe or something, and then there was on page 50, I'm not sure. But open up your books to those problems, and let's just go over any final questions that you might have. Ben? Number 2 on the second part? Okay. So this is relating to this graph, correct? And question number 2, what does question number 2 ask? what is the work function of the metal used? So there are a couple of options here. I'm just going to go first of all with the assumption that you can determine the slope of this line, and you can also read the threshold frequency by looking down here. Now I think I clipped this. It looks like I clipped it from your notes. Can you check to see if this graph matches your graph? It does. So it's got electron volts and the line looks the same, and okay. So I'm looking at that and I'm thinking that that is almost exactly halfway between 4.5 and 5. If it were exactly halfway between 4.5 and 5, then it would be 4.75. I think it's not quite halfway, just by my vision. I would peg that at 4.7 multiplied by 10 to the 14. Now, if you said 4.75, I wouldn't have a quarrel with that. That would be fine. The slope of the line can be found. I actually see two very nice points to read here. Those 2 points. They're right on what I call the crosshairs. And I know that you know how to find the slope, but I'm going to calculate the slope up here myself by taking the rise, which is from 0.2 to 1.1. 1.1 minus 0.2 is 0.9. So the rise is 0.9. And that's EV. The run, I need to go from 5.5 to 9, which is 3.5. 3.5. So your run is 3.5, but don't forget you have to use 10 to the 14, and this is hertz. When you divide when you divide electron volts by hertz, you're going to get electron volts times seconds, because a hertz is a per second. So what I get for the slope is 0.9 divided by 3.5 multiplied by 10 to the 14. So I get 2.57 times 10 to the negative 15. Did anybody do this by doing a regression on your calculator? Is that close to what you got? Pretty close. So, and don't be scared by that, because you know it should be 4.14, right? It should be. But this is an experiment, and it's a hypothetical situation on an exam. So I'm going to record 2.57 times 10 to the negative 15, and the units are, I'm not going to put the units in, but the units of the slope are electron volt seconds, and the units of the F-intercept are hertz. Don't forget, Ben, that this is Planck's constant. So if you want to know the work function, all you have to do is take Planck's constant times the threshold frequency. I know that the work function is given as part of the y-intercept, but mathematically finding the y-intercept might be a little more work than just using the formula work function equals Planck's constant times threshold frequency. As long as you're using the experimental value of Planck's constant and the experimental value of the threshold frequency, it will work. But we are going to be finding the work function in electron volts. And this question asks us to find it in joules. So we have a couple of options. One is to convert that Planck's constant, which is currently, maybe I should write the units in, that Planck's constant is currently electron volt seconds, and this is hertz. So we could convert that Planck's constant, which is the slope, to joule seconds and then multiply by the threshold frequency. I don't quite know why. I'm more comfortable just finding it in electron volts, the work function, and then converting it to joules. So if I multiply by 4.7 multiplied by 10 to the 14 hertz, I get a work function of this many EV. And make sure I get my conversions right, because I screwed that up this morning. I need to multiply by how many joules there are per EV for this to work. So I'm going to multiply by 1.6 times 10 to the negative 19. So I'm getting 1.9 times 10 to the negative 19 joules, roughly.
Yeah, I don't know why I put it equal to 0.95 and then I subtracted that from that and I got a totally different.
Okay. Does that make sense now? Okay. Any other questions? We're going to move on now and take a look at the Compton effect. So you're going to need to turn to the next section in your handout. I realize that my numbering in this unit is all over the place. This should actually be 30.3.13, and it is part 1 of the Compton effect. The next lesson, which is part 2, is mislabeled as part 1. But this is just part 1 of the Compton effect. So we're going to be looking at something called the momentum of a photon. There's something very important about the Compton effect, and it's the same thing that's important about the photoelectric effect, whatever the Compton effect is. And that's that the Compton effect and the photoelectric effect both tell us that light, or EMR in general, behaves like a particle. There's no way to explain the Compton effect without at least talking about light being composed of photons, or X-rays in the case of the Compton effect. And then we're going to solve some problems using today conservation laws, and then continuing tomorrow conservation laws and a special formula for Compton scattering. So there are two competing modern models of EMR. And I say modern because this is what we believe today. There's two viewpoints on what EMR is, or light specifically. One is the electromagnetic wave model, and one is the particle model, or the photon model. So very loosely, the one on the left is a wave model. The one on the right is a particle model. Even though light doesn't really consist of actual particles, those photons are like particles. You're expected to know that it was Maxwell who proposed the electromagnetic wave model. And briefly, just to show that to you, that's the model where he predicted that there's this electric field that oscillates through space, simultaneously creating and being created by a magnetic field oscillating through space. So if you turn on a laser, this is what Maxwell envisions is happening as the light leaves the laser. And you're expected to know that, and that it's credited to Maxwell. The particle or photon model originally started with Planck's idea that energy is quantized, and then Einstein ran with it and said light is quantized. And what that's saying is when you turn on that same laser, it's not an electromagnetic wave. It's not, in fact, a wave at all. It's a series of little drops of light. By the way, there's other experiments you can perform to show that light consists of photons. If you take a dimmer switch, you're all familiar with it, what a dimmer switch is. It makes the light brighter or dimmer. Not a dimmer switch you could buy at Home Depot, but a physics kind of piece of apparatus. And you connect it to a light source, and then you shine that light source on something which detects light hitting it, a light meter. What you discover is that if you turn the light down dim enough, the meter starts dropping and dropping and dropping on your light meter, and then it hits 0. But if you wait, then it goes tick, and it shows something, and it goes back to 0 immediately. And then it shows something again and goes back to 0. And that's direct evidence that what's happening is you've closed the tap so tight on that laser by dimming the switch so much that it's just single photons coming out one after the other. And again, there's a lot of evidence for both of these. In terms of the wave model, it is a fact, an undeniable fact, that EMR, not just light, but EMR will diffract and interfere. So it's an undeniable fact that light behaves like a wave. But light also experiences what's called the photoelectric effect. And the photoelectric effect cannot be explained if you assume light is a wave. And we talked about this when we said that if the frequency of the light is too low, you will never get electrons kicked off. Somebody, I think, even said, well, what if you just shone more light on there to add more energy to those electrons? It doesn't matter because it's a one-to-one electron-photon interaction. So you cannot explain the photoelectric effect without saying light consists of photons. So now let's take a look at what the Compton effect, or actually, my mistake. We're going to review photons for a minute. So what does the photon model of light say? It says that electromagnetic waves or electromagnetic energy is quantized, and the quantum of electromagnetic energy is called a photon. What does it mean to say that you have a photon? It means that for a particular frequency or wavelength of EMR, the light comes in chunks given by these formulas. So whatever you calculate hc over lambda to be, let's say you calculate hc over lambda to be 2 electron volts. That means no matter what I do to that light source, I can only take out of the light source 2 electron volts or 4 electron volts or 6, etc. I can't get 3.2. I can't even get 3. And those are the formulas we use. And this is the point that's going to get a little tricky from here on into the end of the unit. Although photons are not real particles, they behave like particles in that they either exist or do not. And this says you cannot have part of a photon. And the thing about what we're learning today is this statement is not entirely true. We're going to be learning today that we can think of a photon as being partially absorbed, but it only happens under certain circumstances. So I guess I can tell you right now that during the photoelectric effect, if a photon is absorbed, the photon is absorbed. There's nothing left. So when we explain the photoelectric effect, we have to say the photon is either absorbed or not, period. In the Compton effect, it appears as though the photon is partially absorbed. And there will be a qualifier to when that occurs. So now, what is the Compton effect? It's been almost 100 years since it was discovered. Essentially, and this is the difference between the photoelectric effect, and I think it's important. Essentially, you have photons that are going to be striking electrons that are free. In the photoelectric effect, the photons are striking electrons that are not free. They are bonded to atoms. This is an important difference. These electrons are free. They're not bound to atoms. Now, how do we do that? It turns out, and this isn't important for you to actually write, but I just want to put it down here. It turns out that if you take a piece of carbon, carbon is a strange metalloid. It's not really a metal, it's not really a non-metal, but it's an incredibly good conductor. And on the surface of any piece of carbon, the electrons are in a free state. That's not entirely true. Each electron is bound to an atom, but they're continually moving from atom to atom. So we think of the electrons on the surface of carbon as being so loosely bound that they're free. And what I'm literally saying is if you blew across the surface of this with your breath, some electrons are going to be dusted off of the surface. They're just so loosely bound, they're just hanging on barely. So they're free. What Compton discovered is if he used X-rays and he was able to measure the frequency of the X-rays, or the wavelength, it doesn't matter, and he observed what happened when the X-rays hit the carbon target, the X-rays were scattered with a longer wavelength. Just a second here. So what this means is the electrons had a particular wavelength, they interacted with the carbon, and then the wavelength was more. A longer wavelength means less energy. So it makes sense that the X-rays lost energy. But that means they have less photon energy. And that means you're going from a photon with a particular amount of energy to a photon with a different amount of energy. And that means that that photon that hit the carbon lost some of its energy. And this is an apparent contradiction because you're told that photons either exist or they don't. But the world isn't that simple. Visually, what happens, this is a diagram from your text. I've never been a big fan of this, but I get it. Here's the incident X-ray photon. The reason I don't really like this is it's drawn as a wave. But you can also visualize that this is a lump of energy, a photon. And then over here you have a lump of energy. If you look very carefully at this diagram from your textbook, and you determine the wavelength, which is the start from here, up, down, up, the wavelength is this distance. And if you look very carefully over here, the wavelength is from the middle, down, up, up, down. The wavelength now is this distance. So the wavelength in the diagram in your text is increasing. You can think of the energy as being represented by the amplitude of this wave. Even though we're talking about photons, if you imagine that it's a wave, the amplitude is a measure of the energy, and you can see that the amplitude is less. There are other diagrams we can use. This is one that I put together. I don't know why the spheres have that ghostly ring around them. So when you look at the dots and the purple spheres, that represents the electrons and the X-rays. So we have these big X-ray photons coming in. They hit the carbon, they go through the carbon, but when they come out the other side, they have less energy, so they're smaller. I'll tell you right now, and you will learn this over today and tomorrow, the difference between the amount of energy is so slight. If I drew it to scale, you wouldn't see a difference. It's a very, very tiny amount of energy that the photons lose, typically. I've also drawn on here waves. So I'm not a fan of combining a wave and a particle into one picture, like your textbook tries to do. I would rather talk about the particles or photons, which are in purple, or the waves. And you can see that the wavelength afterwards is longer. Okay, there's an increase in the wavelength. And the electrons, which were just sitting there, basically drifting around with no kinetic energy or very little, end up leaving. And it's a very strange thing. You've got gajillions of interactions of photons and electrons in various places where those X-rays hit, and it doesn't matter what the electrons in the metal are doing, they're all scattered in the same direction. You would kind of expect, if you're firing a whole bunch of photons and they're hitting electrons, the electrons would come flying off in kind of random directions. But they don't. They come out at a very specific angle. So I want to read this through with you. According to the most current theories at the time, which included the photoelectric effect, X-ray photons either should be absorbed or not. They should be. But since the X-rays were scattered with a longer wavelength, this was telling Compton that photons could lose some of their energy. And I'll tell you right now, photons can lose some of their energy as long as they collide with a free particle. If they collide with an atom, the photon must be absorbed or not, one or the other. It can't be partially absorbed. So photons can lose some of their energy as long as they collide with what's called a free electron. All right, so this is very similar between the collision, very similar to the collision between a cue ball and an 8-ball, right? It's a two-dimensional collision, really, except it's not a cue ball, it's a photon. During the collision, energy is conserved, but think about this. You have a photon going to hit an electron. Can we produce heat in that interaction? Well, no, because heat is random molecular motion. The only thing of substance is the electron. If I heat up an electron, all that happens is it just goes faster, and we call it kinetic energy. So what is this type of collision called where no heat is produced? Write down in that blank what the name of that type of collision is. This goes back to Unit 1, probably the third or fourth day of the semester. There's a little bit of a hint there because it's called an. Well, I guess I would use an no matter what, whether it's elastic or inelastic. It's elastic. So what does that mean in terms of any kind of analysis that we would do or that Compton did? What it means is if we start analyzing before and after the collision, we have a photon, And this is something that's not exactly true, but you need to try to remember it. In the Compton effect, the electron is at rest to begin with. It's not really at rest, but it is moving on a surface of carbon so slow that its kinetic energy does not amount to much in terms of the total energy in the system. Whereas after the collision, we also have a photon. It's the same photon, apparently. It's just lost some energy, and we have an electron with kinetic energy. So before the collision, and this is not in your notes, I'm just kind of going off the path here and telling you that before we have energy of hc over lambda, and afterwards we have energy of hc over lambda plus the energy of the electron. It's a conservation of energy thing. And to give you some really ridiculous numbers, well, not really ridiculous, but if I told you that the energy of this photon before is 12.0 thousand electron volts, and I told you that the energy of the photon afterwards is 11.992 electron volts, and I said to you, why does the photon have less energy? The answer is that the photon lost some of its energy to the electron. I want to get across to you that this formula at the bottom is not some kind of grand formula that you're going to memorize and rearrange. I'm just saying that if you subtracted the energy of the photon before minus the energy of the photon afterwards, you have to get the energy of the electron. And if you knew those two numbers, then you could also find the speed of the electron. It's more complicated than this, but so far I think that does the trick. So we have a question to answer here. If the electron is scattered by the photon, and the photon loses some energy to the electron, and I know it sounds like I'm almost talking down to you here, but it's going to lead to something which is troubling. If that's the case, then the electron gets kinetic energy. That's no big surprise. But since the electron is now moving, the electron also has momentum. I want everybody to think about where the electron got its momentum from. It's got only one possible answer, doesn't it? It's not like I'm telling you there were other things in there that you couldn't see. The only thing that interacted with the electron was the photon. So the momentum the electron gained must have come from the photon. I mean, where else could it have come from? But what's the problem with that? I want everybody to think about that for a minute. I mean, that's true. There's no other way the electron could have gained momentum other than stealing some momentum from the photon. Why do you think that's a problem, Naya? A little louder, sorry? Photon doesn't have mass. I mean, we started off this whole course, this whole journey that's leading up to some of the stuff we're talking about by saying that the magnitude of the momentum of something is its mass times the magnitude of its velocity, but a photon has no mass. So it certainly changes physicists' outlook at this point in time by saying, you know what? Photons don't have mass, but they behave like they have mass. Now we're starting to get somewhere. We're starting to say, you know what? A photon really does behave like a particle. It isn't just some kind of word that we're going to say that means a bundle of energy. It can push stuff around. When light hits something, it applies a force to it. And one definition of momentum that we've learned about is in terms of impulse. If something can apply a force over time, then the object possesses momentum. And there are demonstrations, and I just forgot to get it out. I will see if I can find it. I have a little demonstration to show you where I shine light on something, and the light pushes it. It actually moves it. So light can exert pressure. Light can exert a force. And that means that photons have momentum. If you were to go back and look at one of the objectives here, it's to understand the principle that photons have momentum. The Compton effect is more evidence that light behaves like a particle. It joins forces with the photoelectric effect and says, you know what? Let's together show everybody that light can behave like a particle. X-rays in this case behave like particles. And not only can they behave like particles, they behave like particles in that they behave like they have mass. If you didn't know better, you would think those little particles hitting something do have mass. You would think they're little bundles, they're little particles like electrons or protons or something else, but they're not. They have no mass. I might show you where these formulas come from, or I might not. I haven't decided. It's not a big deal. Compton developed these formulas using Einstein's E equals mc squared formula, which we will get intimately familiar with in the next unit. But it says the momentum of a photon has a magnitude of Planck's constant divided by the wavelength. Always standard units for these formulas. There is also a formula that relates the energy of a photon to its momentum, and it turns out the energy is equal to its momentum times the speed of light. I want to make it very clear. I might show you in a second where these formulas come from, but they work. When Compton did his experiment and he looked at conservation laws like energy and momentum, and he applied these formulas, it turned out that they accurately predicted the results of his experiment. So these formulas are valid. If you look at your formula sheet under quantum mechanics and nuclear physics, you will see them there, along with two other formulas that you don't know. But the one in the bottom right we will learn tomorrow. The one in the top left we will not learn until next unit. I'll show you quickly how we get these formulas. Okay. If you start off with the idea that momentum equals mass times velocity, and I'm going to dispense with the vectors here and just say magnitudes equals mass times magnitude. And you look at Einstein's formula, E equals mc squared. It's really too bad we don't have a unit on relativity because it's fascinating. There's all kinds of really interesting things. One of the interpretations, that makes it sound like it's not true. One of the true statements regarding this equation is it demonstrates that in our universe, mass and energy are two different forms of the same thing. Okay? What do I mean by that? What I mean is that they're as similar to each other and as different from each other as something like liquid water and ice. Okay? So imagine you being some sophisticated, advanced being on another planet, and you've always lived your life on a tropical planet. You have all kinds of technology, but nobody has ever discovered how to freeze things. The concept of temperatures below zero is impossible for you to imagine. And I come down in my spaceship and I show you a block of ice, which you've never seen before. And you see before your eyes it turning into water, which you have seen before. That would be a very amazing thing. You would not have believed that ice and water are the same thing. It's the same thing with mass and energy. It turns out when you add energy to something, you add mass to it. Which means that when I'm running and I have kinetic energy, I'm more massive. And this is true. The amount that your mass increases when you run is very small. But once you get to around maybe 30% the speed of light, that mass change becomes significant. So that's why on your formula sheet, by the way, they have deltas in front of the E and in front of the M. What this also means is that you can convert mass to energy and energy to mass. I don't know if you recall, you probably don't. When we talked about conservation laws at the beginning of the year, I said something like, you probably remember from junior high, matter is neither created nor destroyed, it merely changes form. And I don't know if you remember, but I told you that's just wrong. You can take matter and destroy it. And what I mean by that is, I don't mean obliterate it. I mean remove it from the universe. It no longer exists. And in its place, you'll have energy. And you can take energy and bring energy into energy, and the energy goes away and you have matter. It's possible to go from matter to energy and back. So what Compton did is he said, if I take this formula and I rearrange it for mass, that means anything with energy has an equivalent mass of E over mc squared. And a photon doesn't have mass, but it has an equivalent energy of this thing, E over c squared. And a photon travels at the speed of light. So v is c. And you can see that one of the speeds of light in that equation on the top and the bottom cancels, leaving you with momentum equals energy over the speed of light, which is this formula in the top right, rearranged. If you were to take this formula here and put hc over lambda in for E, the c's cancel and you're left with momentum equals h over lambda. So this was his idea. He's going to equate the mass of a photon, even though a photon doesn't have mass, he's going to equate it to its equivalent mass from Einstein's formula. And as I said, these two formulas work. They're valid. So we're going to take a look at just a few examples today. Oh, I want to make a point here. When you talk about, look at the bottom of the screen here, when you talk about particles with mass, you have a specific formula for energy and you have a specific formula for momentum. When you talk about photons, you have a specific formula for energy and a specific formula for momentum, and then you have a third formula which includes energy and momentum. What this means is, for a photon, if you know the energy, you can find the momentum and vice versa in one shot. If you knew the energy of a particle, you cannot use that energy directly to find the momentum of the particle. You would have to first solve for v and then use that to find momentum. All right, let's take a look at a few questions. Determine the momentum of each of the following. A 250 nanometer photon. So it's a photon. The only two formulas we can use that have momentum in them for a photon are P equals h over lambda or E equals pc. We have to use P equals h over lambda because we're given lambda. So we take Planck's constant. Again, no electron volts here with these formulas. As he writes electron volts. This is in joule seconds, divided by the wavelength, which is 250 nanometers, so -9. Bless you. It's really a pretty unsatisfying answer. I mean, you're probably sitting there going, yeah, so what? So a photon has this much momentum. We'll get to the real meat of this later in this lesson and also in tomorrow's lesson. But the answer is 2.65 multiplied by 10 to the negative 27. You can use whatever units you want to for momentum. You could use kilograms times meters per second, or you could use newtons times seconds. A photon with a frequency of this number. So think about this. If you want to calculate the momentum using this formula, then you have to get the energy of the photon. And you could certainly do that. We could just go HF equals PC because energy equals HF. You could do that, right? Or you could calculate the energy first, then put it in. If you want to know the momentum using h over lambda, then you can use v equals f lambda first to find the wavelength to put in. It doesn't matter. You either have to calculate the energy of the photon to use the E equals PC formula, or the wavelength to use the h over lambda formula. I'm going to give everybody a minute to pick their option and get an answer. When I take the speed of light, which is the speed of an electromagnetic wave, excuse me, divided by the frequency given in the question, this is what I get for a wavelength. I like using the P equals h over lambda. So I take Planck's constant divided by my calculated wavelength, and I get 5.9 times 10 to the negative 29. Did anybody do it using this idea of finding the energy first? You get the same number, don't you? I hope. So the answer is 5.9 multiplied by 10 to the negative 29 Newton seconds. I guess, in keeping with significant figures, I could put 5.92, but I don't really care. A 10 electron volt photon. Well, this is definitely a case of me wanting to use E equals PC, which means that momentum is the energy of the photon over the speed of light. But I can't use 10 eV for the energy of the photon. I mean, that is the energy of the photon, but I have to use joules. So you have to convert this 10 electron volts to joules and get 1.6 times 10 to the negative 18 joules. Am I right? Okay, so then we can take the energy in joules, which I found by taking 10 electron volts times 1.6 times 10 to the negative 19 joules per electron volt, and dividing by the speed of light. So I get 5.3 times 10 to the negative 27. I'm going to use kilogram meter per second this time just to change things. It can be any appropriate set of units for momentum. D says we have an electron moving at 25% the speed of light. Well, first of all, it's an electron, which means we have to use formulas related to particles with real mass. That's what the phrase I will use often is that an electron has real mass. A photon behaves like it has mass. So the formula we would have to use here to find the momentum of the electron would be P equals mv. Again, we're just interested in magnitude, so I'm going to take the mass of the electron, 9.11 times 10 to the negative 31 kilograms, multiplied by the speed. Well, you're told it's 25% the speed of light, so we can multiply by 25 over 100 times the speed of light. And I'm getting 6.8 times 10 to the negative 23. Anybody else? Okay. And again, I'm just going to go back to Newton seconds. Any appropriate set of units as long as it's appropriate for momentum. Any questions with A through D in that first example? Go ahead. Is it negative 23? Thank you. Can I get a seconder on that? Okay. Thank you, Farhan. So any questions with A through D? All right, number 2. And there's a lot of information in number 2 that we're not going to use to answer 2A, because we're going to answer 2A, then we're going to end the lesson today, practice with some limited applications of the Compton effect. Then tomorrow we'll look at more advanced applications, which is going to involve using some angles. X-rays of a wavelength of 0.24 nanometers are Compton scattered. That means, everybody, that before they strike the electrons, they have a wavelength of 0.24 times 10 to the negative 9. Nano is 10 to the negative 9. If you put that into standard scientific notation, that's 2.400 times 10 to the negative 10. Which kind of makes sense. X-rays are 10 to the negative 10. Now, you might wonder why the importance is placed on all those digits. Why I just don't go 0.24. Well, we'll come back to that a little bit later, but basically because the amount of energy the photon loses is usually very, very tiny, which means the wavelength goes up by a really tiny amount. I don't know what it's going to be. I suspect it's going to be about 2.41 something afterwards, which is pretty typical. So unless you look into that third or fourth decimal place, you would never see the change. So that's before. Electrons and the X-rays are scattered with a particular angle, which we don't care about today. The electrons are scattered with a particular angle, which we don't care about today, but we do care about the speed. So we're ignoring the angles right now. You know the speed of the electrons. So it's possible for you to determine the kinetic energy of each electron. We're always steering in the direction of energy, everybody. This is all about conservation of energy. So in reality, you know what? I don't care what this is. What I care about is what this is. I want to know the energy of the photon before. And you know what? I don't really care how fast the electrons are moving afterwards. I care about their energy afterwards. These are two things we need to know to delve into this problem and solve it, or answer any questions about this situation. So we calculate the kinetic energy using a half mv squared. We calculate EI of the photon using hc over lambda. And for reasons that I will explain later, very soon, I want this done in joules. So I would like everybody to take a couple of minutes and find the kinetic energy that the electron has after it's hit by the photon in joules. I want you to find the energy that the photon has before it hits the electron in joules. Is that speed of the electron times 10 to the 6? Okay. So just to check, are you getting for the initial energy of the photon 8.2875 times 10 to the negative 16 joules? And are you getting 7.57871.878 times 10 to the negative 18 for the kinetic energy of the electron afterwards? Okay. So what are we asked to determine? I mean, I've had you do all this work, and I've been talking a long time about this question. We haven't even looked at what we want. We want to determine the wavelength afterwards. So the thing to note here is that this is a final energy. Right? If you go back and you look at your diagram for the Compton effect in terms of what's actually happening, the before is on the left-hand side of this screen. So the energy before is possessed entirely by the photon, and afterwards the energy is possessed by the photon, which has lost some of its energy, and by the electron, which has gained the energy the photon lost. Do you remember me telling you that this is not drawn to scale because the photon loses not much energy? Take a look at the number that you have for the kinetic energy of the electron. It's in the neighborhood of 10 to the negative 18. And the energy that the photon had is in the neighborhood of 10 to the negative 16. The electron's energy afterwards is only about 1% of the photon's energy before. So this photon is going to keep about 99% of its energy. There's a little sliver that got sliced off of that photon. And what you're doing now is you're saying conservation of energy says the energy that the photon has to begin with has to be equal to the energy that the electron has afterwards plus the energy that the photon has afterwards. And I don't even know that that's... If we had written response questions on exams, I'd really stress this, but I don't even know that that's a big deal to write that down. To me, it makes sense that the photon's energy will be the difference between those two energies we found. We've got this 8.2875 times 10 to the negative 16 joules is going to be equal to 7.5787 times 10 to the negative 18 joules plus the energy of the photon afterwards. So we should be able to calculate the energy that the photon has afterwards. Once we know that, we can figure out what the wavelength is. I've stored these numbers in various places in my calculator, so you can manage that however you need to. This is the energy that I get for the photon afterwards. I get 8.2117 something times 10 to the negative 16 joules. I mean, just look at that. Look at the energy the photon had before, and look at the energy it has afterwards. It's not a lot that's missing. Anyway, what we can do now is set that equal to hc over lambda. And looks like to get lambda, we would have to take hc divided by that energy. Wasn't far off. I thought it'd be about 0.241 nanometers. It's 0.2422. So the wavelength afterwards is 2.422 times 10 to the negative 10 meters. Very, very slight wavelength change between the initial wavelength and the final wavelength. I know that it seems like I shouldn't need to repeat this over and over again, but please make a note, the final wavelength is more. There's a tendency here for people to end up thinking that the wavelength afterwards has to be less because it lost energy, so something lost value. But the wavelength goes up when the energy goes down. So electromagnetic radiation is a wave, electromagnetic radiation is a particle, but electromagnetic radiation is never both at the same time. It's a strange thing. When you shine light through a diffraction grating, it knows that it should behave like a wave. And it does. When you shine light on a photoelectric surface, it knows before it hits. I'm not trying to ascribe some kind of philosophical, metaphysical attribute to light. I'm just using it as an analogy. The light apparently knows that it has to behave like a particle when it undergoes the photoelectric effect or the Compton effect. I'm not sure what this is, but I know there are 10 problems attached. I think there are 10. That's what I would like you to practice on for tomorrow. I think what we'll do, what we should probably do is we'll finish the Compton effect tomorrow. Wednesday we should do the lab, and then we'll finish up the unit Thursday. The lab is more directly related to the particle nature of light, so it will fit better.